Let's start by looking at a schematic of the electromagnetic spectrum. We have the higher energy part of the spectrum with gamma and ultraviolet moving down through optical, infrared, the terahertz, millimeter regime, and microwave, and all the way down into the lower frequency radio. The optical and radio have transparency windows from the ground. Other parts of the spectrum require instrumentation to be in space, or at least at high altitude. And so there are only certain places on planet Earth where we can put our radio telescopes. So we have to place our instrumentation facilities in locations that support those observing windows. A little bit of history. In 1931, Carl Jansky of Bell Labs detected a faint radio hiss that was of undetermined origin at the time. This is the New York Times front page article detailing what he had discovered. And Jansky was ingenious. He determined that the signal tracked the sidereal day, motion with relative to the stars. And he determined that the signal source was the Milky Way galaxy. And he was able to do this by way of a directional antenna that was his own design. He detected his radio waves at a frequency of 20 megahertz. And this was great. Got to see it on the cover of the New York Times. But after that, it really wasn't followed closely by the astronomical community. They thought it was fine, but most people and most professional academics working in astronomy were very much optically based. So nothing happened after that for a while. And, Grote-Reber took some interest in it and built his own dish. There was a faculty at Ohio State who followed up by building his big ear antenna.
Brian,
yes.
I'm sorry. We're only looking at your first slide at the moment.
Oh, okay. I'm clicking on resume share. Here, let me try again. Okay. Can you see that?
Yes, you can see.
Okay. So we were talking about the electromagnetic spectrum and the front page of the New York Times with Carl Jansky, the antenna that he built at Bell Labs, and now we're on this slide here in the start of radio astronomy. So Grote-Reber and John Krause followed up on Jansky's work, but one of the things that really started pushing things forward was what we call the Seacliff interferometer experiment that was conducted by Ruby Payne Scott and collaborators. And I encourage everyone online today to read Miller Goss's book called Making Waves, the story of Ruby Payne Scott. Miller was the director of the VLA for a long time, and he wrote this wonderful history about the beginnings of radio astronomy. In Australia after World War II, there was a lot of antenna equipment left over for people to use, and so they started doing these experiments. So take a look at that book. I've got the link down there with her obituary, and definitely check out Miller's book. So I liked it. We've got at NRAO in Charlottesville, we've got a massive poster of this in one of the hallways. It's titled United States Frequency Allocations, but it gives you an idea about what the electromagnetic spectrum looks like, okay? There's a lot of spectrum in the radio. You've got to consider things for allocations like navigation, mobile communication, aviation, maritime applications. And if we zoom in a little bit further with this area encircled in orange that I have and zoom in, we see even more finely grained sections of the spectrum here, and we start finding areas labeled radio astronomy. You can see here areas designated for things like neutral hydrogen at 1420 megahertz, a very important frequency in radio astronomy. But keep in mind that we make observations everywhere. Due to their redshift, galaxies are shifted to places that may or may not have radio interference. So one of the things that radio astronomers spend a lot of time doing is coming up with creative ways to do our observations, excise the interference, coordinate with the originators of the transmissions, or in some cases, remove data that are unusable. Okay. So this map shows a part of the eastern section of the United States, the National Radio Astronomy Observatory, which was created in Green Bank, West Virginia. Its location is relatively close to what is called the Sugar Grove Station. And this was very important during the Cold War because it would intercept transmissions from other nations that were coming from the eastern seaboard in that direction. So as such, because of Sugar Grove and NRAO, the National Radio Quiet Zone, which you see here highlighted in orange, the NRQZ was created. And in this area, there's restrictions on mobile phone towers, Wi-Fi, microwave usage, in addition to high power radio transmissions. Radio transmissions that are required for first responders are obviously still in use, but anything that is, high power either is not there or must transmit outwards from the square that you see here. So the adventure started in 1956 for NRAO, starting in Green Bank Telescope with the Green Bank facilities. Green Bank, West Virginia, the radio telescopes included the Tattle Telescope, which was home to the original Project Ozma SETI experiment, the 140-foot equatorial mount telescope, which you can which is seen here, as well as a kind of a stopgap measure telescope, which was the 300-foot telescope. That was a transit telescope. Green Bank was also home to the 3-element interferometer that you see on the right-hand side. And this is notable because it was the prototype and testing instrument for the Very Large Array in New Mexico. And I've got a link at the bottom. I'll share these slides with Rodrigo and Mauricio to pass out to everyone in the workshop. But I've got a link there down at the bottom for the NRAO archives. If you're really interested in astronomical history, I encourage you to look at all the documents that are there. So the 300-foot telescope was a incredibly productive instrument as a transit telescope. It lasted well beyond its designed lifetime, worked very well at lower frequencies, but it collapsed in 1986. So nobody was hurt, thankfully. But this is what it looked like in the aftermath after it collapsed one night while it was doing observations. And so this gave rise to the Green Bank telescope. Magnificent unblocked aperture radio telescope, single dish that's fully steerable with a wide frequency coverage. It's a very versatile observing instrument. People use it to study hydrogen in the galaxy, pulsars, water masers in the distant universe. And it's now a key component of the SETI Breakthrough Listen project. And this picture shows the prime focus receiver arm near the top of the telescope antenna, and it's a great thing for visitors to see when they come to the Green Bank Observatory, to actually go up the telescope, up to the dish, all the way up to the top of the receiving arm, and have a look around. Spectacular view, and it's just a lot of fun to climb on radio telescopes. So today, NRAO has multiple sites, including the administration and engineering development in Charlottesville on the University of Virginia campus. That's where I work. But we also have Green Bank and the Science Operations Center in Socorro, New Mexico, which is home to the Very Large Array. So the Carl Jansky Very Large Array, located in New Mexico, just celebrated its 40 years of science and innovation with a conference last week. It continues to be the world's most versatile mid-frequency radio interferometer ever since it was dedicated in 1980. I imagine a lot of the people here online today are younger than that. So, but we're going to talk about the future of the Very Large Array as we get closer to the end of the talk. So I've got a link here at the bottom with a video that we made. We actually got to fly over the array. Aviation is another one of my interests. And a couple years ago, the telescope was in a kind of a maintenance mode, and so everything was shut down, and we were able to fly over it, which was actually quite exciting to do. The antennas in this image are positioned in their most compact D configuration. Okay, so lower resolution when they're in that configuration, but the array can actually be moved to different configurations. Again, here it's in the D configuration, and this is done by way of a transporter, which moves the telescopes along these rails to different stations. So the versatility in the very large array is that it can be used in different configurations depending on the goals of the astronomer, what their observing objectives are, and what kind of phenomena you're actually observing. The VLA covers mid to low frequencies. But returning to our view of the electromagnetic spectrum, some astronomical phenomena need to be observed in the millimeter, okay? So this plot shows the zenith transmission. So closer to 1 means that the emission comes through, 0 means the atmosphere is opaque at that frequency. Where was this measured? Northern Chile and South America. So we've got Santiago and southeast of San Pedro de Atacama in the little inset picture. At 5,000 meters in the Atacama Desert of Sierra Chattanantor, in the highest, driest place on Earth, astronomers can take advantage of these observing windows with ALMA, the Atacama Large Millimeter Submillimeter Array. It's the largest high-frequency radio telescope to the world and home to the highest altitude supercomputer. So make sure that you visit the ALMA and North American ALMA Science Center websites to learn more about how to use this facility and what kinds of science that you can do with it. You can see this supercomputer, that's what we call the correlator in these photos. The ALMA facility is jointly operated by the NRAO, the European Southern Observatory, ESO, and the National Astronomical Observatory of Japan, NAOJ. And the way ALMA is organized is that there are ALMA regional centers, or ARCs, in countries around the world, including in Charlottesville, Virginia. So here's another panoramic view of the correlator at the high site where the telescope is. NRAO also operates the very long baseline array called the VLBA with 25-meter antennas located across the United States, the Virgin Islands, and Hawaii. This array comprises the highest resolution astronomical instrument ever built. So here's some images of the VLBA antenna sites going all the way from the Virgin Islands to Hawaii. And the VLBA can actually be used in conjunction with other telescope facilities as well, sometimes single dish telescopes, to build a high sensitivity array. So it depends on what kind of observations you want to do. NRAO is also a world-class leader in instrumentation development. Our engineers and research scientists, they research, design, build, and test and deploy the receivers, the correlators and back ends, and all the electronics for the telescope facilities that we've been talking about. And we have research and development activities both in Charlottesville and Socorro. And you see folks here working in the laboratory, and also one of the higher frequency receivers on the right-hand picture. And I want to point out, if you're interested about the history of radio astronomy, very much specific to NRAO, I'm going to point out 2 books. One was written by and edited by a number of scientists at Green Bank, Jay Lockman, Frank Gigo, and Dana Balser, and it's entitled "But It Was Fun: The First 40 Years of Radio Astronomy at Green Bank," because we can all agree that radio astronomy certainly is a lot of fun. You can actually get the book online on Frank's website there on the link on the lower left-hand side. And then more recently, Ken Kellerman, who's one of the senior astronomers at the NRAO, and Ellen Boughton wrote a book called Open Skies, all about the history of the National Radio Astronomy Observatory. And so I've got a link to that book there down in the lower right-hand corner. So if you're interested, they're both wonderful reads, and you can find out all about the history. So let's take a look at some images. This is the Crab Nebula, 2 kiloparsecs from planet Earth. It's a supernova remnant with a neutron star at the center. This was imaged with the BLA. This rapidly rotating neutron star is actually called a pulsar. We'll talk about pulsars here in just a second. Here's another example. This is probably familiar to a lot of you. This is the, I'm going to go back here. This is actually CAS-A, 3.4 kiloparsecs away. VLA observation. This is the Crab Nebula, 2 kiloparsecs from Earth. This is the supernova remnant with a neutron star at the center. And then this is what I want to get to. This is Messier 87. These are new observations from a variety of telescopes that you see on the right-hand side. The left-hand side shows a Hubble Space Telescope image. But this is the fantastic micro arc-second resolution image in the lower right-hand corner from ALMA and other telescopes around the world, showing the black hole that's at the center of this galaxy at the Virgo cluster, which is something that I've always been interested in studying. So we talked about CAS-A, M87, the Crab Nebula, and then I've got another image on here for 3C273. And if we go look in any radio astronomy book and we plot the spectra of these objects, the continuum spectra, they have a decreasing slope associated with them. Okay, this is a common commonality that all these objects have, and it's plotted here against objects like the Sun and the Orion Nebula, which have a different slope associated with it. So the flux versus frequency, if we plot these for things like Cygnus A, CAS-A, Virgo A, also known as M87, we find that the slope varies between 0 and 2 for most radio galaxies and quasars. This is due to the synchrotron emission of these objects, and hold that thought in your mind. We're going to return to that here in just a moment. Here are spectra from another one of Ken Kellerman's reviews for extragalactic objects. And you see they can have a variety of different types of structure to them. And this is dependent on what kind of galaxy quasar that you're looking at. But again, you have the decreasing slope of the spectra in these objects. So let's return to the Crab pulsar. The Crab pulsar has a spin frequency of around 30 hertz. This is a 3D diagram that I made that shows the shape of what a pulsar magnetosphere would look like. And the Green Bank telescope, which we've talked about, has enormous success in discovering pulsars. Radio telescopes can also study phenomena via spectral line transitions of atoms and molecules, the simplest element in the universe, which is something that I study. Hydrogen emits at a frequency of 1420 megahertz due to the spin flip transition of hydrogen. So we can use hydrogen as a tracer of distance to galaxies. We can determine their structure of their neutral gas, map their dynamics. The picture that you see here is an optical image of the spiral galaxy Messier 51 that's located 9.5 megaparsecs from Earth. The blue shows the neutral hydrogen mapped with the Very Large Array, where we see not only the gas in the disk of the galaxy, but a large tidal tail that's extending well beyond the disk of the galaxy. A little bit closer to us is the galaxy Messier 33, located a bit under 1 parsec from Earth. It has a large extended disk that you again see colored here in blue of neutral hydrogen, mapped with the Very Large Array. This is one I really like. This is Messier 82, again mapped with the Very Large Array. This is from one of the scientists at NRAO, Josh Marvel, and one of our graphic designers, Bill Saxton. And if we look at a spectrum of M82 and plot the radio and far infrared flux versus frequency, we see a number of features that have a commonality in normal galaxies. We have at the low frequency extending just below 1 gigahertz up to roughly a frequency of around 30 gigahertz, we find that it's dominated by the synchrotron emission. As we move to higher frequencies, the dominant factor that you see here is the free emission. And then as you increase in frequency and go to shorter and shorter wavelengths up into the far infrared, the dominant factor is the dust, okay? So we can examine moving to higher frequencies with the ALMA telescope in South America, shown here under the South Celestial Pole. We can look at the molecular gas content of a pair of galaxies that are known as the antennae galaxies, NGC 4038 and 4039. The spectral line of CO at 115 gigahertz is shown here in red. So this, combined with other observations, allows us to study the star formation potential and history of galaxies. And the incredible resolving power of ALMA also allows astronomers to study protoplanetary disks like HL Tau. So this object is located 140 parsecs from Earth. The image of the disk has changed what we know about planet formation, and surveys with the telescope are being conducted to gather statistics on these planetary disks. Moving back to the Green Bank telescope, this image of high velocity gas being ejected from the Milky Way galaxy was actually mapped with the GBT. So these are high velocity clouds that are in orbit around our own Milky Way galaxy. And we talked about tuning your instrument selection to the kind of observation that you want to do. And because of its unblocked aperture and because of its large size, but it has this, it is just a single dish, it's very well matched to studying neutral hydrogen in and around the Milky Way galaxy. So speaking of Milky Way, this is an image that I took at the Palomar Observatory in California. Here we're looking towards Sagittarius in the center of our galaxy. And this was what it looks like mapped in the continuum with a radio telescope. Okay. Beautiful, large continuum features here along the galactic plane. Returning to objects beyond our Milky Way, here's a VLA image of Fornax A. This is 19 megaparsecs from Earth. This incredibly bright radio source does not have particularly active jets, so you see that yields a diffuse look that you can see in this image, but still massive structures in the universe. A more recent image that was created by Bill Cotton and his collaborators, an astronomer at NRAO. This image of Hercules A was obtained with all 4 configurations of the VLA. So I mentioned that the VLA can be moved on rails to different configurations. In this particular case, these observations took many years to make. Is that they would do the observation in one configuration, wait for the telescope to be moved, take more observations. And what this allows you to do is bring out all sorts of different kinds of diffuse structures that you see in this image. So a new project from the NRAO that I have a little bit of involvement in is the VLA Sky Survey. So this is a 3 gigahertz continuum survey that will cover the entire sky that is visible from New Mexico. These are some of the high resolution images that were produced by the first pass of the survey. It recently, what we call the quick look images. These are available freely online to the astronomical community. And the white scale bars that you see in each image indicates 30 arc seconds. And on the right-hand side are just some rough numbers and statistics about the frequency coverage of the survey, what its angular resolution is, the area of the sky that's going to cover. The website is in the upper left-hand corner. I encourage you to go look at that website and check out some of the data. And also its publication from last year detailing the factors and different intricacies of the observing scheme, what the data products are going to be, is in a paper published in PASP by Mark Lacey and collaborators. So I'd encourage you to have a look at that paper. And this is what you get with the VLA Sky Survey. The original NRAO VLA Sky Survey, which was done at L-band, is shown on the left-hand side. The first survey, which was higher resolution, is shown in the middle. So you go from knowing that there is an astronomical object there that you can measure the radio flux on, to the middle picture where you see, okay, there is some structure here to this object, better resolution. And then the VLA Sky Survey, the state of the art, is on the right-hand side, where you now resolve an object like this into 2 separate components, okay? Close to 10 million objects will be cataloged by the VLA Sky Survey. And again, check out the websites that I have in my slides to go take a look at some of the data. But we've got a lot of young people here listening today, and we want to talk a little bit about the future of radio astronomy. So this lies in future facilities like the Next Generation Very Large Array. So these telescopes that they're planning to build will extend all over North America, with concentrations in the American Southwest. So the green dots that you see here in the lower right-hand corner are the location of the current Very Large Array. But you can see we're going to put hundreds of radio telescopes. This will be the central core here, okay? 1/2 kilometer for scale. And then in this spiral pattern across New Mexico, and then extending across the southeastern United States into Mexico, state of Texas, Arizona, over hundreds of kilometers to give it that superior resolution. It's going to be a spectacular instrument. Just this past week, there was a press release that the funding has been awarded by the National Science Foundation to build the prototype. I'd encourage you to go look at the news release here and find out all about what that is going to involve and what the telescopes are going to look like. So one of the other things that I work with at the NRAO is our student programs, and I'm sure Mauricio and his fellow students have talked to you about the NRAO 9 program, where we talk a lot about software and coding and what kinds of skills are needed to succeed in data science and radio astronomy, and how to enable the next generation of software and tool builders. So I've got the link to the NRAO 9 program there. But I also want to talk about other student opportunities. So one of the things, and I'll put these links in the chat window, and you can also get them from our slides, is to subscribe to the NRAO electronic newsletter. You'll get a monthly email talking about all different kinds of opportunities for science, for students, for technical innovation, and that's the best place to get the latest and greatest. Also to follow NRAO on social media, Twitter, Instagram, and Facebook. I've also got a link here to our student programs. Okay, so definitely check those out. Our National Astronomy Consortium is a wonderful program that is run every summer, but really all year long, with opportunities for students. A new initiative that NRAO is taking part in and leading is the Radio Astronomy Data Analysis Lab, RADIO. This is a new initiative from NRAO that I would encourage you to read about, and what kinds of skills that observatories are looking for in the future. As you move through your careers, we have a great program called ALMA Ambassadors that is offered by the NRAO. And then 2 other resources. I've given you a very short introduction today to you all about the NRAO, but every other year the NRAO operates the Aperture Synthesis Summer School. Fortunately, these talks and tutorials are posted online in both video form, along with all of the slides for the science and technical program. So definitely check that out. Plenty of things to watch there to learn specifically about interferometry and how you use telescopes like the VLA, ALMA, and the VLBA. And finally, a book that was published by 2 of our astronomers, Essentials in Radio Astronomy. There's an online version of it as well, and I've got a link to that site down there at the bottom. So I will finish by going to my last slide. I want to thank the NRAO EPO folks, Jeff, Bill, and Sophia, for all their wonderful images, a number of which I used in this presentation. To our NRAO 9 program, Lindell and Anya, who worked with me on that. And finally, thanks to Flor for her wonderful translation skills and helping me out today to be able to translate this into Spanish. Greatly appreciate that. And thanks for listening. And either Mauricio or Rodrigo or whoever's in charge right now, I'm happy to take any questions.